1 billion years have passed since the birth of the universe. A billion years of quiet expansion. 8 billion years of stars flickering into existence, dying, and seeding the cosmos with the elements that will shape everything yet to come. In our previous journey, we drifted through the dawn of cosmic structure, the rise of the first galaxies, watched ancient star clusters awaken, and drifted across the cosmic web as gravity slowly sculpted the universe into its earliest forms. Those first galaxies were small, fragile, and chaotic, yet they were the beginning of everything. Now, the universe has grown older, wider, brighter, and far more complex. In this chapter, we enter the age of giant galaxies, a time when small, early galaxies collide, merge, and transform into immense cosmic cities of stars. The universe is no longer dim and scattered. It is alive with luminous spirals, glowing nebulae, and supermassive black holes that blaze like cosmic beacons. Quasars ignite at the centers of young galaxies, releasing torrents of light powerful enough to be seen across billions of light years. Star formation surges to its peak, filling the cosmos with newborn light. Everywhere, galaxies gather into clusters and superclusters, forming the sprawling architecture of the modern universe. Yet, despite the brilliance, this epoch remains calm in its own vast cosmic way. Gas drifts gently through intergalactic space. Star fields shimmer quietly in ancient spirals. Gravity moves with patience, shaping galaxies over hundreds of millions of years. Tonight, we drift once more, slowly, peacefully, through the universe's expanding masterpiece, that universe entering its greatest era of creation. Day universe on the verge of maturity. Close your eyes, breathe deeply, and float with me into the cosmic night. $1 billion years. Day threshold crossed. Day, transformation complete. The universe had traveled an enormous distance from its origins in the Big Bang, not just through space, but through complexity, through organization, through the gradual emergence of structure from primordial simplicity. The cosmos at this milestone was unrecognizable compared to its infancy. Where once there had been only smooth, nearly uniform darkness broken by scattered points of light, now there were galaxies. Millions of them, spread throughout the observable universe like cities across a continent, each one a concentration of billions of stars, vast clouds of glowing gas, and dark matter halos binding it all together. This was no longer the chaotic, turbulent universe of the first few 100 million years. The era of the first stars, those massive, short-lived population ethery giants had passed. The violent proto-galactic storms, where small dark matter halos collided and merged in constant chaos, had begun to calm. The universe was entering a new phase, one of greater stability and organization, though still far more active and dynamic than the cosmos we see today. Think back to where we began. In the first moments after the Big Bang, the universe was a hot, dense plasma, protons, electrons, and photons all mixed together in a state of thermal equilibrium. As it expanded and cooled, neutral atoms formed, and the cosmos entered what we call the Dark Ages. No stars. No galaxies. Just hydrogen and helium gas slowly collapsing under gravity into the first dark matter halos. Then came the first stars, igniting perhaps 200 million years after the Big Bang. These giants blazed brilliantly but briefly, living only a few million years before exploding as supernovae. Their death seeded the universe with heavy elements, carbon, oxygen, iron, that would fundamentally change how gas behaved and how future stars would form. From those enriched clouds came the second generation of stars. Population spies nor snala and longer lived. These stars clustered together in the deepest gravitational wells, forming the first proto-galaxies. And as gas continued to flow inward along dark matter filaments, these proto-galaxies grew, merged and evolved into the first true galaxies. Now, at the 1 billion year mark, the transformation was complete. The scattered proto-galaxies had coalesced into recognizable galactic structures. Galaxies now had cores dense stellar bulges at their centers, where millions of stars orbited in complex patterns. Many had disks too, rotating structures of gas and stars flattened by angular momentum. Some were showing the first hints of spiral structure, though nothing as organized as the grand spirals we see in the modern universe. The fog that had obscured the early universe had lifted completely. Reionization, the process by which ultraviolet light from the first stars and galaxies ionized the neutral hydrogen filling space, was essentially finished. The intergalactic medium was now transparent to most wavelengths of light. Photons could travel vast distances without being absorbed, carrying information about distant galaxies across billions of light years of space. Light now filled the cosmic web. If you could have observed the universe from some godlike vantage point, able to see across its entire volume, you would have seen a magnificent structure. Filaments of glowing galaxies stretching across hundreds of millions of light years, like luminous threads woven through the darkness. Dati intersections of these filaments, dense nodes blazed brilliantly proto-clusters where dozens or hundreds of galaxies gathered. And between the filaments, vast voids sat nearly empty, dark regions where few galaxies had formed. This cosmic web, the largest scale structure in the universe, was becoming more apparent with each passing million years. The initial density fluctuations from the Big Bang, infinitesimal variations in the distribution of matter, had been amplified by gravity over hundreds of millions of years. Overdense regions had become more overdense, attracting matter from their surroundings. Underdense regions had become more underdense, emptying out as their gas flowed toward higher density areas. The result was a hierarchical structure of extraordinary beauty and complexity. Dark matter formed the skeleton invisible filaments and halos that created the gravitational scaffolding. Normal matter, the hydrogen and helium that makes up stars and gas, followed that scaffolding, accumulating in the deepest wells. And wherever sufficient gas accumulated, stars formed, creating the visible galaxies we can observe. But the universe at 1 billion years was still young in many ways. The galaxies were smaller than their modern descendants. The Milky Way today contains hundreds of billions of stars and has a mass of perhaps 1 trillion solar masses, including dark matter. But its progenitors at this epoch would have been much smaller, perhaps a few billion stars, masses of tens of billions of solar masses, spread across multiple proto-galactic fragments that would eventually merge to form the modern galaxy. Star formation rates were high, much higher than today. The universe was rich in cold gas, the raw material for making stars. This gas was being funneled along filaments toward galaxies, providing a constant supply of fuel. Then the galaxies themselves were efficient at converting that gas into stars. Dotas, the typical star-forming galaxy at this epoch, might form tens or even hundreds of solar masses of new stars every year, compared to just 1 or 2 solar masses per year in the modern Milky Way. The stellar populations in these early galaxies were also different from what we see today. His hose. Because the universe was younger, the oldest stars in any galaxy were only a few 100 million years old. Distant relatives were only young and hot by stellar standards. Unlightably time-tethered by stellar standards. Kotor's OS standards. Kotor, Yedivianev of his Trova, fast a Washington. Talon, Kotor. It more self-enlived. Kolthastasha and Thlikan Druboris Keretio. You'd chess was you colored off. There were no ancient red giants, no white dwarfs billions of years old. The stellar populations were dominated by young, blue stars, massive O and B stars that burn hot and bright. And the chemistry was still evolving. While the first supernovae had enriched the gas with metals, the metallicity, the fraction of mass in elements heavier than helium, was still low compared to modern values. Double typical star forming region might have a metallicity 1/10 or 1/100 that of the Sun. This lower metallicity affected everything from how stars formed to the properties of planetary systems. Yet, despite their youth and differences from modern galaxies, these billion-year-old galaxies were recognizably the ancestors of the systems we see today. They had established the fundamental structures, cores, disks, halos. They had begun the process of chemical enrichment that would continue for billions of years. They hosted supermassive black holes at their centers, seeds that would grow into the billion solar mass monsters we observe in giant galaxies today. The universe had crossed a threshold. The transition from the first stars to the first galaxies was complete. The cosmic web had emerged from the primordial darkness. Light and structure filled the cosmos. And now, as the universe passed its billionth birthday, it was ready to enter what might be called its golden age, Jan epoch of peak star formation, of galaxy growth and evolution, of increasing complexity and beauty. This golden age would span the next few billion years, from about 1 billion to about 4 billion years after the Big Bang. During this time, the universe would build most of the stellar mass that exists today. Galaxies would grow through mergers and gas accretion. The most massive structures, giant elliptical galaxies and rich galaxy clusters, would begin to assemble. And the cosmic web would become ever more defined and massive. But we're getting ahead of ourselves. That at the 1 billion year mark, these developments were just beginning. The universe had established its foundation. Now it would build upon that foundation, creating ever more complex and magnificent structures. Let's explore how that happened, step by step, starting with the growth of the galaxies themselves. Galaxies at 1 billion years were diverse in size and structure. but most were small by modern standards. The typical galaxy might contain 1 billion to a few billion stars substantial, but far from the 100 billion or more found in giant spirals and ellipticals today. These galaxies were the building blocks, the raw material from which larger structures would eventually form. The growth of massive galaxies proceeded through two primary mechanisms, both of which operated simultaneously throughout this epoch. The first mechanism was mergers, collision and coalescence of smaller galaxies into larger ones. The second was gas accretion, the continuous infall of fresh hydrogen from the cosmic web, feeding ongoing star formation. Let's start with mergers. In the dense, crowded conditions of the early universe, galaxy collisions were common. Galaxies weren't scattered in isolation as many are today. They formed in groups and clusters, in the nodes and along the filaments of the cosmic web, where the spatial density of galaxies was high. And in such crowded environments, close encounters and collisions were inevitable. When two galaxies of roughly comparable mass approached each other, the interaction unfolded over hundreds of millions of years in a complex gravitational dance. First, as they drew close, their gravitational fields began to influence each other. Tidal forces, differential gravitational pull across the extent of each galaxy, distorted their shapes. Spiral arms, if present, became more pronounced. Stars and gas in the outer regions were pulled outward, forming tidal tails that stretched behind each galaxy like cosmic streamers. As the galaxies interpenetrated during their first passage, they didn't simply merge immediately. Instead, they passed through or alongside each other, their dark matter halos and stellar populations overlapping briefly. The gas, however, couldn't interpenetrate as easily. When gas clouds from the two galaxies collided, they created shocks regions of sudden compression and heating. These shocks could trigger intense bursts of star formation, as compressed gas clouds collapsed and fragmented into stars. After the first passage, the galaxies would separate again, pulled apart by their orbital motion. But gravitational interaction had stolen orbital energy, converting it to random motion and heat. The galaxies were now bound to each other, destined to fall back together. On. The second passage, the interaction was even stronger. More tidal distortion, more gas shocks, more triggered star formation. The galaxies began to lose their original shapes, their stellar populations becoming increasingly scrambled. Multiple passages might occur over hundreds of millions of years, each one bringing the galaxies closer as they radiated away orbital energy through dynamical friction and gravitational wave emission. Eventually, the cores of the two galaxies merged at the center of the combined system. The final coalescence was rapid and violent, with gas funneled toward the merged core, triggering a massive starburst period of incredibly intense star formation that might last just a few tens of millions of years, but produce billions of new stars. The end result of a major merger between two disk galaxies was typically an elliptical galaxy, a spheroidal system with stars moving in random orbits rather than an organized rotating disk. The merger scrambled the orderly rotation of the original disks, converting the kinetic energy of ordered rotation into random motion. The stellar population became more uniformly distributed, with stars on chaotic orbits filling a roughly ellipsoidal volume. These merger-formed ellipticals were some of the first massive galaxies in the universe. By combining two or more smaller galaxies, they could reach masses of hundreds of billions of solar masses, genuinely massive systems by any standard. And they were concentrated in the densest regions, the protoclusters where merger rates were highest. But not all mergers were between equals. Nine-my mergers, where a large galaxy captured and absorbed a much smaller companion, were even more common. In these interactions, the small galaxy was gradually torn apart by tidal forces as it orbited the larger one. Its stars were stripped away and scattered into a diffuse halo around the primary galaxy. Its gas might be funneled toward the center, triggering a modest burst of star formation, but nothing like the spectacular starbursts of major mergers. Minor mergers allowed galaxies to grow gradually, adding mass bit by bit over hundreds of millions of years. A large galaxy might absorb dozens of smaller satellites over cosmic time, each one adding to its stellar mass and enriching its halo with tidal debris. This process continues even today. The Milky Way is currently in the process of absorbing several dwarf galaxies, including the Sagittarius dwarf elliptical, whose tidal stream wraps around our galaxy like a ribbon. The second major mechanism of galaxy growth was gas accretion. Even in the absence of mergers, galaxies could grow by capturing fresh gas from the cosmic web. This gas flowed along dark matter filaments toward galaxies, channeled by gravity like water flowing downhill. When it reached a galaxy, it added to the galaxy's gas reservoir, providing fuel for future star formation. In the early universe, this gas accretion was particularly efficient. The filaments were rich with pristine hydrogen, and the gas was relatively cool tens of thousands of degrees, cool enough to be captured by a galaxy's gravitational well. Some of this gas fell directly onto the galactic disk, where it could quickly fragment and form stars. Dollars of weaved Gorgon include 90 sectate minimum proesting. And two things gas cares, if that's catch me wanting to cut ages care. The rate of gas accretion depended on several factors. Darlot's Galaglac, with deeper gravitational wells, could capture more gas. Galaxies located on major filaments, where gas flow was strongest, received more fuel than those in sparser regions. And galaxies in very dense environments, like the centers of clusters, might actually lose gas to ram pressure stripping as they moved through the hot intracluster medium, even as they gained mass through mergers. T-Cont, Voyager, mergers and drove dramatic galaxy growth between 1 and 4 billion years after the Big Bang. Chief sent Riotent, you hadn't mergered. He named Charles Greyer features Huodice of Town Uin. He won a erosive game. Careful Wapus. He told the Pontic Kefras and was romance restored in this that seat that. Lentinada plus is elegant seats. Vate Timmy's procluster me. Senses gabble or triple their stellar mass during this period. Small, irregular galaxies merged into larger spirals. Spirals merged into ellipticals. And the most massive galaxies, in the densest environments, grew into giants containing hundreds of billions of stars. But this growth wasn't uniform. General LSCs in different environments evolved differently. In the densest protoclusters, mergers dominated, and most galaxies were transformed into ellipticals. In less dense regions, galaxies could accrete gas steadily and maintain their disk structures, growing into large spirals. And in the voids, the underdense regions between filaments, galaxies remained small and grew slowly, starved of both merger partners and accreting gas. The morphology of galaxies, their shapes and structures, was being determined during this epoch. The fundamental dichotomy we observe today between spiral galaxies with rotating disks and elliptical galaxies with random stellar orbits was established by the different pathways of growth and evolution. Then that dichotomy was intimately connected to environment, where a galaxy formed and evolved determined what it would become. That as galaxies grew, their internal structure also evolved. The earliest galaxies had been chaotic, with thick disks, massive clumps of star formation, and little organized structure. But as they matured, they began to settle into more stable configurations. Disks thinned as random motions dissipated. Star formation became more evenly distributed, rather than concentrated in massive clumps. And in some galaxies, beautiful spiral structure began to emerge. The formation of spiral arms is a complex process involving density waves regions, where stars and gas are temporarily compressed as they orbit the galaxy. These density waves rotate around the galactic center like spokes on a wheel, and as gas clouds enter them, they're compressed, triggering star formation. The newly formed stars illuminate the spiral arms, making them visible as bright blue-white regions tracing out graceful curves. But in these early epochs, spiral structure was often transient and chaotic rather than the long-lived, well-defined spirals we see in modern galaxies. Massive gas clumps and high star formation rates created gravitational disturbances that constantly rearranged the disk. Spirals would form, persist for a few tens of millions of years, then dissolve as the underlying mass distribution changed. It would take billions of years for galaxies to develop the stable, persistent spiral arms characteristic of grand design spirals like M51 or M81. Elliptical galaxies, meanwhile, were developing their own distinctive features. After forming through mergers, they began to relax, their stellar populations settling into a configuration that reflected the galaxy's mass distribution and rotation. Most ellipticals have little to no net rotation, with their stars moving on random orbits that fill an ellipsoidal volume. But some ellipticals, particularly those formed from less extreme mergers, retained significant rotation, creating fast rotating ellipticals that are more flattened and disc-like. Tonstral regions of ellipticals became particularly dense, creating the massive bulges we see today. These bulges are old stellar populations, formed in the intense starbursts accompanying galaxy mergers. The stars are typically red and yellow colder, cooler stars that have exhausted or are slowly exhausting their hydrogen fuel. By contrast, spiral galaxies have smaller bulges or no bulge at all in some cases, and maintain ongoing star formation in their disks, keeping their stellar populations younger and bluer. By the Vaughan time, the universe reached 2 or 3 billion years of age. A clear morphological sequence had emerged. Gigi habas, even first all carcrows of life ceased to dent, or cap dist den exexthicate, a thay brushes use quip, that's down. overwald emotion od flyg espenta smuslin, by the avalors, taskanat kurd. Light spags, iklas hawer thalajet viewer. Two elliptical galaxies dominated the densest regions, the cores of clusters. Spiral galaxies were more common in moderate density environments. Irregular galaxies, small systems with chaotic structure and ongoing star formation, were found throughout, but were most common in low-density regions and as satellites of larger galaxies. This morphology-density relation is one of the fundamental patterns in the galaxy distribution we observe today. And it was established during this epoch, between 1 and 4 billion years after the Big Bang, as galaxies grew and evolved through mergers and gas accretion, their fates determined by their environments and their interactions with neighbors. The growth of massive galaxies was not just a story of increasing size, but of increasing complexity. Early proto-galaxies were simple systems, just stars and gas in a dark matter halo. But as galaxies grew and evolved, they developed structure cores, disks, bulges, halos, spiral arms. They developed dynamics, rotation, random motion, streaming motions in spiral arms. They developed chemistry metallicity gradients from center to outskirts, varying stellar populations of different ages and compositions. But by the end of this growth phase, around 4 billion years after the Big Bang, the universe contained a rich variety of galaxies ranging from small, irregular dwarfs to massive ellipticals and grand spirals. The foundation laid in the first billion years had blossomed into something magnificent and diverse. And at the centers of many of these galaxies, something truly extraordinary was happening: the ignition of quasars. The name itself evokes mystery at point short for quasi-stellar radio source, a technical term from the 1960s when these objects were first discovered. Astronomers found point-like sources of radio waves that looked like stars in visible light, but had completely bizarre properties. Their spectra showed emission lines shifted to much redder wavelengths than expected, indicating they were extraordinarily distant. Yet, despite being billions of light years away, they were bright enough to be detected from Earth, which meant they had to be incredibly luminous, outshining entire galaxies from a region no larger than our solar system. WA now understand that quasars are powered by supermassive black holes with masses of millions, billions, or even tens of billions of times the mass of the Sun, residing at the centers of galaxies. When matter falls toward these black holes, it forms an accretion disk, and the gravitational energy released as matter spirals inward is converted to light with extraordinary efficiency. A supermassive black hole, accreting at high rates, can outshine all the stars in its host galaxy combined, creating the brilliant beacon we see as a quasar. The era of quasars peaked between 1 and 4 billion years after the Big Bang. This was when supermassive black holes were growing most rapidly, fed by the gas-rich conditions of the early universe. And it was when quasars were most numerous, with the quasar density reaching its maximum around 3 billion years after the Big Bang. Let's understand how this happened. In the first billion years, as we've discussed, the seeds of supermassive black holes were planted. Stellar, Mass black holes formed from the deaths of massive population or DA stars. Some of these sank to the centers of proto-galaxies and began accreting gas, growing gradually. Others may have formed through direct collapse, creating intermediate mass black holes of thousands of solar masses from the start. These seed black holes grew through a combination of gas accretion and mergers with other black holes. Each time, two galaxies merged, their central black holes eventually merged as well, creating a more massive black hole. And whenever the galaxy captured gas, whether through steady accretion from the cosmic web or through merger-triggered inflows, some of that gas would funnel to the center and feed the black hole. By 1 billion years after the Big Bang, the most massive black holes had reached masses of millions or even billions of solar masses. They sat at the centers of the most massive galaxies, which were typically located in the densest regions of the cosmic web, the protoclusters and the nodes where multiple filaments intersected. Now, in the period from 1 to 4 billion years, these black holes entered their phase of most rapid growth. 10 SL factors, no solgraptron into dream, stoned heightbox are treated growth, disjunction, lesvision, Weitstudon. The question to Trestro, should store heightwise, and tend into two this. First, the universe was still rich in cold gas. The filaments of the cosmic web channeled enormous amounts of hydrogen toward galaxies, and galaxies had not yet converted most of this gas into stars. There was plenty of fuel available. Second, galaxy mergers were very common during this epoch. When two gas-rich galaxies merged, the interaction funneled vast amounts of gas toward the center of the merged system. This gas formed an enormous accretion disk around the central black hole, feeding it at rates that might approach or even exceed the Eddington limit, the theoretical maximum rate at which a black hole can accrete before radiation pressure from the accretion disk becomes strong enough to blow away the infalling material. Third, the black holes had reached masses where their gravitational influence extended over large regions. Taminyon's solar mass's black hole has a gravitational sphere of influence, the region where its gravity dominates over the rest of the galaxy, that extends to dozens or hundreds of light years. This large sphere of influence allowed it to capture gas efficiently from its surroundings. When a supermassive black hole accretes rapidly, the result is spectacular. The accretion disk, compressed and heated by friction and gravitational forces, reaches temperatures of millions of degrees in its inner regions. At these temperatures, the disk glows brilliantly in ultraviolet and X-ray light. The spectrum is distinctive blue-white continuum from the thermal emission of the hot disk, with broad emission lines from gas clouds orbiting at high velocities near the black hole. The total luminosity can be staggering. A quasar at the peak of its activity might have a luminosity of 10 trillion times the Sun equivalent to 100 or 1,000 entire galaxies. And because this light is emitted from a region no larger than our solar system, the accretion disk around a billion solar mass black hole has a radius of only a few light days. The surface brightness is extraordinary. If you were somehow able to observe a quasar from nearby, say, from a distance of a few thousand light years, it would appear as a blindingly brilliant point of light, far outshining everything else in the sky, bathing planets in searing radiation. The light from quasars travels across vast distances of intergalactic space. Because these objects are so luminous, we can detect them even when they're extremely far away, billions of light years distant, corresponding to look-back times of billions of years. When we observe a distant quasar, we're seeing light that left it billions of years ago, giving us a window into the early universe. In fact, quasars are among the most distant objects we can observe. The most distant quasars known are seen as they were less than 1 billion years after the Big Bang, when the universe was just 5 or 10% of its current age. The light from these quasars has travelled for over 13 billion years to reach us, stretched to infrared wavelengths by the expansion of the universe. The era of quasars was a time when the universe was, in some sense, brighter than it is today. Not because there were more stars, actually. The total stellar luminosity would be lower than today, since most stars hadn't been born yet. But because of the intense emission from active galactic nuclei, the universe had more point-like sources of extreme brightness scattered throughout it. If you could have travelled through the universe during this epoch, you would have seen quasars everywhere. Not as densely packed as stars in our night sky, but as you looked out across the cosmic web, you would see brilliant points of light marking the locations of actively accreting supermassive black holes. Some would be in the centres of visible galaxies, the galaxy's light overwhelmed by the glare of the quasar. Others would be so distant that only the quasar itself would be visible, the host galaxy too faint to detect. The environmental effects of quasars were profound. The radiation from a quasar ionizes gas over enormous volumes, creating ionized bubbles extending for millions of light years around the quasar. Within these bubbles, the intergalactic medium is heated to tens of thousands of degrees by photoionization. The quasar's light can suppress star formation in nearby galaxies by heating their gas and preventing it from cooling and collapsing. But quasars don't just emit light. They also drive powerful winds and jets. Radiation pressure from the intense light of the accretion disk can accelerate gas to velocities of thousands of kilometers per second, creating broad absorption line winds that carry enormous amounts of mass and energy away from the quasar. These winds plow into the surrounding gas of the host galaxy, heating it, stirring it, and in many cases, expelling it entirely from the galaxy. Jets are even more dramatic. Detail, in some quasars, magnetic fields threading the black hole itself become twisted and amplified by the disk's rotation. The greatest lawyer, amplified by the disk's rotation. These magnetic fields can launch narrow jets of material from the poles of the accretion disk at velocities approaching the speed of light. The jets are composed of electrons, protons, and magnetic fields, all moving together in a collimated beam. When a jet plows into the surrounding gas, whether the interstellar medium of the host galaxy or the more diffuse intergalactic medium, it creates an enormous shock front. The shocked gas is heated to tens of millions of degrees, hot enough to emit X-rays. The shock accelerates some particles to extremely high energies, creating cosmic rays that emit radio waves as they spiral in magnetic fields. The result is enormous radio lobes, diffuse regions of radio emission extending millions of light years on either side of the quasar. These radio-loud quasars, as they're called, are some of the largest single objects in the universe. The radio lobes can span distances greater than the diameter of 10 galaxies lined up end to end. And the total energy contained in these lobes, the energy needed to heat all that gas and create all those cosmic rays, can be equivalent to the rest mass energy of millions of suns, converted entirely to energy through Einstein's E-may, represents billions of years of black hole accretion, with a fraction of the infalling mass converted to energy and injected into the jets. The feedback from quasars, both the radiation and the winds and jets, played a crucial role in regulating galaxy formation. When a quasar ignited in the center of a galaxy, its energy output could heat and expel much of the galaxy's gas, shutting down star formation. This quenching of star formation could transform a blue, actively star-forming galaxy into a red, quiescent one in just a few 100 million years. This feedback also established a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. Today, we observe that the mass of a supermassive black hole is tightly correlated with the mass of the galaxy's central bulge and with the velocity dispersion of stars in the bulge. This correlation suggests that black holes and galaxies grew together, regulating each other's growth through feedback processes. The era of quasars gradually declined after about 4 billion years after the Big Bang. The quasar density peaked and then began to fall as the universe aged. Several factors contributed to this decline. Gas was being depleted, converted into stars, expelled from galaxies by feedback, or simply spread out by cosmic expansion. Merger rates were declining as the universe expanded and galaxies became more spread out. And many black holes had already grown to large masses and consumed much of the available gas in their vicinity. But by the time the universe reached about 7 or 8 billion years of age, halfway to the present, the quasar era was essentially over. Most supermassive black holes had entered a quiescent phase, with only occasional feeding events when gas strayed close enough to be captured. The universe became dimmer in the sense of having fewer of these extremely bright point sources, though it was growing brighter in total stellar light as more and more stars accumulated over time. Today, quasars are rare. Most supermassive black holes, including the one at the center of our own Milky Way, are dormant or only weakly active. At Sagittarius **, the Milky Way's central black hole with a mass of about 4 million solar masses, currently accretes only tiny amounts of material and produces minimal luminosity. But in the past, during the quasar era, it may have blazed much more brightly when gas was more abundant and the Milky Way underwent mergers with other galaxies. The light from quasars during their peak epoch has been traveling through space ever since they emitted it. Some of that light is still traveling, stretched to longer wavelengths by cosmic expansion, and will continue traveling for billions more years before it finally reaches some distant galaxy. Quasars from the peak epoch are among the most distant objects we can observe, their light providing a unique probe of the early universe. They tell us about the growth of supermassive black holes, about the gas content and chemistry of early galaxies, about the structure of the intergalactic medium through which their light travels. Beyond this fascination, in spectra of quasars, astronomers can detect the absorption line of sight, creating what's called the Lyman Alpha Forest, a forest of absorption lines that maps out the distribution of neutral hydrogen across cosmic time. The era of quasars was a crucial phase in cosmic evolution. It was when supermassive black holes grew to their present-day masses. It was when feedback from active galactic nuclei began to significantly affect galaxy evolution. DI was when the brightest sustained sources of light in the universe shone across cosmic distances. And it was a golden age of activity and energy that has no parallel in the modern, more sedate universe we inhabit today. While galaxies were growing and quasars were blazing, the underlying structure of the universe, the cosmic web, was also evolving and strengthening. This vast network of filaments, nodes, and voids is the scaffolding upon which all cosmic structure is built. And during the period from 1 to 4 billion years after the Big Bang, it became increasingly massive, increasingly defined, and increasingly influential in shaping the distribution and evolution of galaxies. The cosmic web is made primarily of dark matter, that mysterious substance that makes up about 85% of all matter in the universe, but interacts only through gravity. 1A24s and can't see dark matter directly because it doesn't emit, absorb, or scatter light. It that squatty. It need of gravitating because it doesn't emit. But we can see its gravitational effects, the way it bends light through gravitational lensing, the way it holds galaxy clusters together, the way it shapes the large-scale distribution of galaxies. The web formed through gravitational instability, acting on the initial density fluctuations left over from the Big Bang. The earliest moments after the Big Bang, quantum fluctuations during inflation created tiny variations in density regions that were slightly more or less dense than average. These variations were incredibly small, just 1 part in 100,000, but they were the seeds from which all structure would eventually grow. The universe expanded and cooled. These density variations began to grow through gravitational instability. Overdense regions attracted more matter from their surroundings, becoming more overdense. Underdense regions lost matter to their neighbors, becoming more underdense. This process accelerated over time, with the contrast between dense and sparse regions increasing exponentially in the early universe. But the growth didn't happen uniformly in all directions. The initial density field had structure on many scales, with overdensities and underdensities of various sizes and shapes. When these regions collapsed gravitationally, they did so anisotropically, more rapidly in some directions than others. The result was a network of structures with different geometries. The densest regions collapsed first and most completely in all 3 dimensions, forming nodes, or at least spherical or ellipsoidal concentrations of dark matter that would eventually host galaxy clusters. Less dense regions collapsed primarily along 2 dimensions, forming sheets or walls flattened structures where matter accumulated but didn't reach the highest densities. Then the least dense, overdense regions collapsed along only 1 dimension, forming filaments, thread-like structures connecting nodes and sheets. The underdense regions, meanwhile, expanded along with the universal expansion but didn't accumulate matter. They became voids, vast regions of space containing few galaxies and little matter, surrounded by walls and filaments, but largely empty within. This hierarchical structure, nodes, sheets, filaments, and voids, is known as the cosmic web, and it was becoming increasingly clear and massive between 1 and 4 billion years after the Big Bang, as matter continued to flow from voids toward filaments, from filaments toward nodes, driven by gravity's inexorable pull. The filaments of the cosmic web served as highways for gas flow. Hydrogen from the voids and from diffuse regions between filaments streamed toward the filaments themselves, channeled by the gravitational potential created by the dark matter. Once in the filaments, the gas flowed toward nodes, following the paths of steepest gravitational gradient. This process is called cold flow accretion, and it was extremely important for galaxy formation during this epoch. The gas flowing along filaments remained relatively cool tens of thousands of degrees because it was dense enough to cool efficiently through radiation, even as it was being heated by gravitational compression. This cool gas could be captured directly by galaxies, falling onto their disks and providing fresh fuel for star formation. Simulations of galaxy formation show these cold flows as thin streams of gas winding through the larger scale structure, connecting the cosmic web to individual galaxies. A galaxy located on a major filament might have multiple streams flowing into it from different directions, like rivers converging on a lake. The gas would spiral inward through the galaxy's dark matter halo, eventually reaching the galactic disk, where it would cool further, fragment, and form stars. The mass of the cosmic web was growing not just through this reorganization of existing matter, but also through the capture of matter that had previously been more uniformly distributed. In the earliest universe, matter was nearly smoothly distributed. But as structure formed, an increasing fraction of matter became concentrated in filaments and nodes, with the voids becoming increasingly empty. By 4 billion years after the Big Bang, perhaps half of all the ordinary matter in the universe was located in filaments and sheets of the cosmic web. Another significant fraction was in nodes, the densest regions that would become galaxy clusters. Only a small fraction remained in the voids, and that fraction was decreasing as cosmic time passed. The strengthening of the cosmic web had important implications for galaxy formation and evolution. Galaxies on major filaments, with strong gas inflows, could maintain high star formation rates for longer periods. They grew more massive than galaxies in sparser regions, and they were more likely to merge with neighbors, since galaxies tended to cluster along filaments. The nodes of the cosmic web, the densest regions where multiple filaments intersected, became the sites of forming galaxy clusters. By 1 billion years after the Big Bang, protoclusters containing dozens of galaxies had already formed in the densest nodes. Over the next few billion years, these protoclusters would grow into massive clusters containing hundreds or thousands of galaxies. The formation of galaxy clusters was intimately tied to the cosmic web. As filaments channeled gas and galaxies toward nodes, the mass in those nodes increased. The increasing mass deepened the gravitational potential, which attracted even more matter, creating a runaway process. The densest nodes became increasingly dominant, growing into the massive galaxy clusters that are the largest gravitationally bound structures in the universe. Within these forming clusters, the environment was dramatically different from the field, regions between filaments where individual galaxies lived in relative isolation. Dim clusters, galaxies were packed closely together, their gravitational interactions frequent and strong. Dot gas between the galaxies, the intracluster medium, was heated to tens of millions of degrees by shocks and by energy injected from galaxies and active galactic nuclei. This hot intracluster medium affected galaxy evolution in several ways. Galaxies moving through it experienced ram pressure stripping, losing their cold gas and having their star formation quenched. The hot gas itself was too hot to be captured by galaxies and turned into stars, effectively removing a reservoir of potential star-forming material. And the high-temperature environment favored the survival of massive elliptical galaxies, which had already converted most of their gas into stars over star-forming spirals. The cosmic web also determined the large-scale distribution of galaxies. The galaxies weren't randomly distributed through space. They traced out the filamentary structure of the web, creating a pattern visible in large galaxy surveys. When astronomers map the positions of millions of galaxies in 3 dimensions, the cosmic web becomes strikingly apparent, a lacy network of filaments and sheets surrounding empty voids. This structure exists on enormous scales. Individual filaments can stretch across hundreds of millions of light years. The Sloan Great Wall, one of the largest known structures, is a vast sheet of galaxies extending over 1 billion light years. Voids can be tens or hundreds of millions of light years across enormous regions, containing few or no bright galaxies. The cosmic web is not static. It continues to evolve as matter flows and as structures grow through mergers. Filaments grow thicker and more massive. Nodes accumulate more matter and become more dominant. Voids expand and become increasingly empty. This evolution will continue for billions of years into the future, though it's gradually slowing as cosmic expansion accelerates due to dark energy. Beyond pestering back different epochs, by studying how its properties have changed over cosmic time, astronomers can test theories of structure formation and constrain cosmology of Bulplayamigli Beeringlau. Matus to fossil record of the initial conditions from the Big Bang and of the subsequent action of gravity. 2. Trischellenfum dubbed the nature of dark matter, about the initial density fluctuations, about the expansion history of the universe. Universe significant versi, slag je mo's breath of light. Zoals de universie, clodus breathsa, vinus of refashion, power frighted to acute cabia ferration, like hiders with elix dizzled. Langsy to do with fate, festering out the strengthening of the cosmic web between 1 and 4 billion years after the Big Bang set the stage for all subsequent cosmic evolution. DAT established the large-scale distribution of matter. DAT2's determined the height and outspin quitting. The planned from underfoot neat created the network of gas flows that fed galaxy formation. And it sculpted the universe into the beautiful, complex structure we observe today, a structure whose basic architecture was laid down in those early billions of years. the universe experienced its most intense era of star formation. This period, sometimes called cosmic noon, was when the universe was building stars at the highest rate in its history. The cosmic star formation rate, the total mass of stars formed per year in a given volume of space, reached its peak around 3 billion years after the Big Bang, about 10 times higher than the rate today. To understand why star formation peaked during this epoch, we need to consider several factors. First, gas availability. The universe was still rich in cold, dense gas, the raw material for star formation. Much of the hydrogen created in the Big Bang was still in gaseous form, not yet locked up in stars. Then this gas was being efficiently channeled toward galaxies along cosmic web filaments, providing a steady supply of fuel. Second, galaxy merger rates. WT, as we've discussed, galaxy mergers were much more common during this epoch than today. When gas-rich galaxies merged, the collision compressed their gas, triggering intense starbursts. These merger-driven starbursts contributed significantly to the overall cosmic star formation rate. Third, the efficiency of star formation. That gas in early galaxies was somewhat less efficient at forming stars than gas in modern galaxies due to lower metallicity and higher temperatures. But the sheer abundance of gas more than compensated for this slightly lower efficiency. Galaxies had enormous gas reservoirs relative to their stellar mass, allowing sustained star formation over hundreds of millions of years. Individual star-forming galaxies during cosmic noon were extraordinary objects. Best, typical actively star-forming galaxy might convert tens or even hundreds of solar masses of gas into stars every year, 10 to 100 times the rate in the modern Milky Way. The most extreme starbursts, triggered by major galaxy mergers, could reach star formation rates of 1,000 solar masses per year or more, creating billions of stars in just a few tens of millions of years. These high star formation rates had dramatic observational consequences. Star-forming regions glowed brilliantly in ultraviolet light from hot young stars. The ultraviolet radiation ionized surrounding hydrogen, creating enormous high regions, ionized nebulae that emit characteristic pink-red light from hydrogen emission lines. These nebulae could be thousands of light-years across, far larger than anything seen in the modern nearby universe. Massive stars formed in these starbursts burned through their fuel quickly and exploded as supernovae within just a few million years. The supernova rate in intensely star-forming galaxies could reach 1 per year or higher, meaning that on average, a star exploded somewhere in the galaxy every year. These constant explosions injected enormous amounts of energy into the interstellar medium, heating it, stirring it, and driving powerful galactic winds. The most extreme star-forming galaxies of this epoch have been detected through observations in infrared and submillimeter wavelengths. These dusty star-forming galaxies, or DS-phages, are shrouded in thick clouds of dust that absorb ultraviolet and visible light from young stars and re-emit it as infrared radiation. The dust, heated to temperatures of a few tens of degrees Kelvin by the stellar radiation, glows brilliantly in the infrared, making these galaxies some of the most luminous objects in the universe. Date to WT. Dusty star-forming galaxy might have a total infrared luminosity of 1 trillion solar luminosities or more, as bright as 100 Milky Ways, all from star formation. All from star formation. Treat as 100 Milky Ways, all from star formation. Yeah. Biggest mil jour, some recount latter he might date to pass. It I heed. For an applying colour fast, most of this luminosity comes from a region just a few thousand light years across, creating an incredibly intense starburst. The conditions in these galaxies are extreme gas densities, thousands of times higher than in the Milky Way, temperatures of hundreds of degrees Kelvin, turbulent velocities of tens to hundreds of kilometers per second. Star formation during cosmic noon was creating most of the stellar mass that exists in galaxies today. Even though this epoch lasted only a few billion years, the high star formation rates meant that a significant fraction, perhaps half of all stars ever formed, were born during this period. The universe was converting gas into stars at a prodigious rate, building the stellar populations we see in galaxies today. The types of stars formed were similar to those forming today, now that metallicity had increased to significant levels. The era of pure population E-stars formed from gas with only trace amounts of metals had passed. By cosmic noon, typical gas metallicities were perhaps 1/3 to 1/2 of solar metallicity, sufficient to allow the formation of stars across a wide range of masses. Massive stars, those more than 10 times the mass of the Sun, formed in large numbers and dominated the light from star-forming regions. These stars are short-lived but incredibly bright, each one outshining thousands of sun-like stars. They produce copious ultraviolet radiation, ionizing the surrounding gas and creating the brilliant nebulae that characterized star-forming galaxies during cosmic noon. Intermediate mass stars, from a few solar masses to 10 solar masses, formed in even larger numbers. These stars live for hundreds of millions to a few billion years and contribute significantly to the total light from a galaxy after the most massive stars have died. Many of these intermediate mass stars are still alive today in old galaxies, having evolved into red giants. Dollo mass stars, comparable to the Sun or smaller, formed in the largest numbers but contribute least to the total light because they're individually dim. However, they're crucial for the long-term evolution of galaxies because they live for billions or even trillions of years. Low-mass stars formed during cosmic noon are still on the main sequence today, burning hydrogen and contributing to the light of galaxies. And the smallest stars, red dwarfs, less than half the mass of the Sun, formed in enormous numbers. These stars are so faint individually that they're difficult to observe, but they're thought to outnumber more massive stars by factors of 10 or more. Red dwarfs live for trillions of years, far longer than the current age of the universe, meaning that every red dwarf ever formed is still alive today. The peak of cosmic star formation also corresponded to peak production of heavy elements. Massive stars, which die as supernovae, are the primary source of elements like oxygen, silicon, sulfur, and iron. The high star formation rates during cosmic noon meant high supernova rates, which meant rapid enrichment of the interstellar and intergalactic medium with metals. Gas metallicity increased substantially during this epoch. Dating at 1 billion years after the Big Bang, typical gas metallicities were perhaps 1/10 of solar. during 5 times de jour, views of ovation, perhaps 1/10 of solar. Certainly, the Poundwaldwa from the Hedus Sakun, companion quicksilk out by 4 billion years, they had increased to 1/3 or even 1/2 of solar in many star-forming regions. With the regions, suffect guys throughout, air of Sebinju. With the roots preferred Jeshi, it is 4D club pick-a-back of gins. Episode Demanul billion to hits. Don Vernia, Sevdi Sunpia, Sevding Rizet Convo is Yuk, is the bedding, Buski at 1 krone. Bring cruel some there at Kibirioth, and there's the. This increasing metallicity affected everything, from the efficiency of star formation to the properties of stars themselves to the types of planetary systems that could form. The nebulae that formed during cosmic noon were among the most beautiful structures in the cosmic sky. Vast clouds of glowing hydrogen, illuminated by clusters of brilliant young stars, stretched across thousands of light years. These nebulae had complex structures, pillars and globules, where dense gas resisted ionization, shells and bubbles blown by stellar winds and supernova explosions, shock fronts where expanding bubbles collided. DI, if you could have observed in kind of these nebula planet, the sight would have been spectacular. The sky would glow with diffuse pink and red light from hydrogen emission. Brilliant blue-white stars would be scattered throughout, some individually visible, others merged into glowing star clusters. Dark lanes of dust would thread through the nebula, silhouetted against the glowing gas. And if you watched over millennia, you'd see the structure evolving, bubbles expanding, new stars igniting, supernovae flashing briefly then fading. But the era of peak star formation could not last forever. Even during cosmic noon, there were signs that star formation would eventually decline. Von Seebeck, from star formation itself, stellar winds, supernova explosions, ionizing radiation, was heating and dispersing gas, making it harder for future generations of stars to form. Dagan feedback from quasars was expelling gas from galaxies, removing fuel for star formation. And cosmic expansion was making the universe less dense, reducing the rate at which gas flowed along filaments toward galaxies. By about 4 billion years after the Big Bang, the cosmic star formation rate had peaked and begun its long decline. The decline was gradual. At first, star formation rates remained high for another 1 billion or 2 years. But the trend was clear. The universe's era of maximum productivity, when it was building stars at the highest rate, was coming to an end. However, the legacy of cosmic noon persists to this day. Most of the stars in old galaxy synapticals and spiral bulges formed during this epoch. The chemical enrichment that occurred continues to affect stars forming today. And the structures created during this era, massive galaxies, galaxy clusters, the large-scale distribution of matter, are still visible in the universe around us. Star formation continues today, of course, but at a much reduced rate. The modern universe forms stars at perhaps 1/10 the rate during cosmic noon. Day S is less abundant. Merger rates are lower, and much of the available gas has already been converted to stars. The universe has calmed down, entering a more sedate phase where star formation proceeds more gradually. But for a few glorious billion years, The universe blazed with the light of newborn stars. The era of peak star formation was a golden age of cosmic creativity, when the universe built most of the stellar mass that lights up galaxies today. As the cosmic web strengthened and galaxies grew, some regions stood out as particularly dense and massive, the nodes where multiple filaments intersected, the deepest gravitational wells in the universe. These regions were becoming galaxy clusters, the largest gravitationally bound structures in the cosmos, systems containing hundreds or thousands of galaxies, all held together by their mutual gravity. The formation of galaxy clusters is a hierarchical process, beginning with small groups of galaxies and building up through mergers and continued accretion to create the massive clusters we observe today. DTR 1 billion years after the Big Bang, true rich clusters didn't yet exist. But protoclusters, dense concentrations of dozens of galaxies occupying relatively small volumes, had already formed in the densest nodes of the cosmic web. These protoclusters were the ancestors of modern galaxy clusters like the Coma cluster or the Virgo cluster, which contain thousands of galaxies and have masses of a quadrillion solar masses or more. But at this early epoch, they were smaller, less organized, and still actively assembling through rapid infall of galaxies and gas. The growth of galaxy clusters proceeded through several mechanisms. First, galaxies forming in and near the protocluster would fall inward, drawn by gravity toward the cluster center. The dark matter halos of these galaxies merged with the larger scale dark matter halo of the cluster, adding to its total mass. Then the galaxies themselves became members of the cluster, their motions now determined by the cluster's gravitational potential rather than just their own motion through the cosmic web. Second, smaller groups of galaxies would merge with the protocluster. A group containing 5 or 10 galaxies might fall into the cluster as a unit, its galaxies remaining associated with each other even after joining the larger cluster. Over time, the galaxies in the infalling group would disperse throughout the cluster, but initially they could be identified as a substructure, a clump of galaxies within the larger cluster. Third, the protocluster would accrete gas from surrounding filaments. As gas flowed along filaments toward the cluster, it would be shock heated upon entering the cluster's deep gravitational potential. Infalling gas would collide with gas already in the cluster, creating shock fronts that heated the gas to temperatures of tens of millions of degrees, hot enough to emit X-rays. This hot gas became the intracluster medium, or ESMR, tenuous plasma filling the space between galaxies within the cluster. Despite being extremely hot, the ICM is also very diffuse, with densities thousands or millions of times lower than the best vacuums we can create on Earth. Nevertheless, because clusters are so large, typically a few million light-years across total mass of the ICM is enormous, often exceeding the total mass of all the stars and all the stars and all the cluster galaxies combined. The ICM plays a crucial role in cluster evolution. Its high temperature and pressure prevent it from cooling and forming stars, effectively sequestering a huge reservoir of baryonic matter in a form that can't participate in star formation. The IIMSO affects galaxies that pass through it. The ROS, moving through this hot gas, can strip cold gas from galaxies, quenching the stardarses, catching their star formation. moving through this hot gas from galaxies of Arian seas. Frina Neunster I handelssoft. The times are connected to these eggs. Fater Alex gases rotate the respiratory thresh in it like Lorcan is it more agreed death. By 2 to 3 billion years after the Big Bang, recognizable galaxy clusters had formed in the densest regions. These clusters contained hundreds of galaxies within volumes a few million light-years across. The member galaxies were moving at high velocities, typically a few hundred to 1,000 kilometers per second bound by the cluster's gravity, but on complex orbits that took them through and around the cluster over billions of years. The central regions of these clusters were dominated by massive elliptical galaxies. These had formed through multiple mergers and had grown into giants containing hundreds of billions of stars. The largest of the brightest cluster galaxies, or Betelgeuse, often sat at or near the center of the cluster's gravitational potential, marking the bottom of the potential well where galaxies and gas naturally accumulated. Betelgeuse are special objects. They're among the most massive galaxies in the universe, with stellar masses often exceeding 1 trillion solar masses. They formed through the merger of multiple large galaxies, with each merger adding stars and creating a larger, more massive system. Betelgeuse are elliptical in morphology, with extended stellar halos, and they often show evidence of recent or ongoing accretion of smaller galaxies' tidal streams and shells in their outer regions, marking the remains of disrupted satellites. Surrounding the Betelgeuse, other massive ellipticals orbited in the cluster core. These galaxies had also grown through mergers, though not to the same extreme sizes as the Betelgeuse. They had high stellar masses, old stellar populations, and little ongoing star formation, having exhausted their gas supplies through a combination of star formation, Agon feedback, and ram pressure stripping by the ISM. Therefore, from the cluster center, the galaxy population became a teen addition to ellipticals. There were cirro or lenticular galaxy systems with disk-like structures but little gas and low star formation rates. These S0 galaxies may have been spirals that had their gas stripped as they fell into the cluster, transforming them from actively star-forming systems into quiescent ones, while preserving their disk structure. And in the outskirts of the cluster, true spiral galaxies could still be found, systems that had recently fallen into the cluster and hadn't yet had their gas completely stripped. These galaxies were often asymmetric or disturbed, showing signs of interaction with the cluster environment. Over time, they would be transformed, losing their gas and joining the population of quiescent galaxies in the cluster core. The distribution of galaxies within clusters wasn't random. Galaxies were concentrated toward the cluster center, with the number density of galaxies increasing as you approached the core. This reflects the gravitational potential galaxies that formed earliest or fell into the cluster first had time to sink toward the center through dynamical friction, a process where gravitational interactions with other cluster members gradually remove orbital energy and cause a galaxy to spiral inward. The dark matter in clusters formed an extended halo encompassing all the galaxies and gas. This dark matter halo was the most massive component of the cluster, typically accounting for about 85% of the total mass. The dark matter couldn't be directly observed, but its presence was evident from the gravitational effects, high velocities of galaxies, the temperature of the ICM, and gravitational lensing of background galaxies. Gravitational lensing occurs when light from distant galaxies passes through or near a massive cluster. The cluster's gravity bends the light, creating distorted, magnified images of the background galaxies. Sometimes, this produces beautiful arcs and rings, highly magnified images of distant galaxies stretched and curved by the cluster's gravitational field. But by studying these lensed images, astronomers can map out the distribution of mass in the cluster, including the dark matter that dominates its mass. Galaxy clusters are more than just collections of galaxies. They're interconnected systems where the galaxies, hot gas, and dark matter all interact and influence each other. Galaxies orbit through the cluster, sometimes passing through the core, sometimes swinging out to large distances before falling back. As they move through the ICM, they leave wakes, trails of disturbed gas marking their passage. The ICM itself circulates within the cluster, driven by various processes. Gas falling into the cluster creates bulk flows inward. At the centers of massive galaxies inject energy, creating bubbles that rise buoyantly through the IMM. Galaxy motions stir the gas, creating turbulence. Cluster mergers. When two clusters collide and merge, create enormous shocks that heat and compress the gas. These cluster mergers are among the most energetic events in the universe since the Big Bang. When two galaxy clusters collide, the process unfolds over billions of years. Initially, the clusters approach along a cosmic filament, each one a massive concentration of galaxies, gas, and dark matter. As they draw closer, tidal forces begin to distort them, pulling out streams of galaxies and gas. At first contact, the dark matter halos interpenetrate, passing through each other because dark matter interacts only gravitationally. But the hot gas from each cluster's ICM collides, creating enormous shock fronts that heat the gas to even higher temperatures, sometimes over 100 million degrees. These shocks can span millions of light years and release energy equivalent to trillions of supernovae. Meanwhile, the galaxies themselves mostly pass through each other unscathed. Space between stars is so vast that direct stellar collisions are extremely rare even when galaxies interpenetrate. But the gravitational field becomes incredibly complex, with tides and perturbations affecting galaxy orbits and potentially triggering starbursts in some galaxies. After the first passage, the clusters separate briefly before falling back together, similar to what happens in galaxy mergers, but on a much larger scale. Multiple passages may occur over billions of years before the clusters finally merge completely, creating a single larger cluster with a combined mass, mixed galaxy population, and disturbed, shock-heated ICM. But by 4 billion years after the Big Bang, the largest galaxy clusters had masses approaching a quadrillion solar masses and contained hundreds of member galaxies. These were the most massive structures that had achieved gravitational equilibrium, reached a state where they were no longer rapidly accreting or merging, but had settled into a relatively stable configuration. These clusters marked the nodes of the cosmic web, the places where the web was most dense and most visible. A map of galaxy clusters traces out the large-scale structure of the universe, with clusters aligned along filaments and walls, separated by vast voids. The formation of galaxy clusters represented a milestone in cosmic evolution. In truth, it showed that the universe had developed structure on the largest scales if gravitational instability, acting over billions of years, had created bound systems containing me, one it set the stage for the future evolution of galaxies. Because environment matters. Jesse tu singer de 72 overly, complete seas. You see here, the non solastry. Ik hoopvult, de sea for his sea, and can set the stipe for the night town at her temp of Kongbua, who towards to Damakik, but no hout, be a sur chef. But depth, yours heat. From every galaxies and clusters evolved differently from galaxies in the field, shaped by ram pressure stripping, frequent interactions, and the dense, hostile environment of the cluster core. Even today, 14 billion years after the Big Bang, galaxy clusters remain the largest bound structures in the universe. They're natural laboratories for studying gravity, dark matter, hot plasmas, and galaxy evolution. Damned, they're beautiful structures. Whether observed in visible light showing the distribution of galaxies, in X-rays revealing the hot ECM, or through gravitational lensing mapping the dark matter distribution. The rise of galaxy clusters between 1 and 4 billion years after the Big Bang was a crucial chapter in cosmic history, when gravity assembled the largest cities in the cosmic metropolis. The universe was becoming chemically richer with each passing million years. Between 1 and 4 billion years after the Big Bang, the cosmic abundance of heavy elements, everything heavier than helium in astronomical parlance, increased dramatically. This chemical enrichment was one of the most important transformations of this epoch, with profound implications for the future evolution of stars, planets, and ultimately life itself. Let's understand what we mean. The Big Bang produced only the lightest elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. Everything else, carbon, nitrogen, oxygen, silicon, iron, gold, uranium was created inside stars through nuclear fusion or in the violent explosions that mark stellar death. These heavy elements, called metals, by astronomers regardless of their actual chemical properties, were then ejected into space where they mixed with the primordial gas. In the first billion years, the first generation of stars, population the air, began this enrichment process. Their deaths as supernovae spread carbon, oxygen, and other elements into their surroundings, creating pockets of enriched gas. The second generation, population E of stars, formed from this slightly enriched material and continued play process, each generation building on the work of the previous one. Now, during cosmic noon, when star formation rates were at their peak, chemical enrichment accelerated dramatically. Billions of massive stars were being born every year across the universe. And massive stars are the primary engines of chemical enrichment. They burn through their nuclear fuel quickly, fusing hydrogen into helium, helium into carbon and oxygen, and continuing up the periodic table through neon, magnesium, silicon, sulfur, and finally iron. When a massive star exhausts its fuel, it collapses and explodes as a supernova. The explosion synthesizes additional heavy elements through rapid neutron capture and explosive nucleosynthesis. The blast wave then ejects both the elements created in the star's core during its lifetime and those created during the explosion itself, spreading them across hundreds or thousands of light years. The supernova rate during cosmic noon was extraordinary. In intensely star-forming galaxies, supernovae might explode at rates of 1 per year, or even higher. In the universe as a whole, millions of supernovae were detonating every year, each one enriching the interstellar medium with several solar masses of heavy elements. Different types of supernovae contributed different elements. Core collapse supernovae, the deaths of massive stars, were the primary sources of oxygen, neon, magnesium, silicon, and sulfur. These elements are produced by fusion in the stellar core and are ejected when the core collapses and the outer layers rebound in the supernova explosion. The typical core collapse supernova might eject a solar mass or more of oxygen alone. TP supernovae, the molecular explosions of white dwarf stars in binary systems, were the primary sources of iron and nickel. These explosions completely disintegrate the white dwarf, converting most of its mass into iron peak elements through explosive carbon and oxygen burning. A type Ia supernova produces about half a solar mass of iron, along with other iron peak elements like cobalt and nickel. Destroyens doldu ostridas that mecans stratos supernovaes, elements gold, platinum, uranium, and other elements beyond iron that require neutron-rich environments to form, and other elements beyond iron now to form. When two neutron stars spiral together and merge, the collision ejects a small amount of extremely neutron-rich material that undergoes rapid neutron capture, building up the heaviest elements in the periodic table. All of these enrichment processes were operating at high rates during cosmic noon. The high star formation rates meant high supernova rates. The large number of stellar binaries meant frequent type Ia supernovae. And the large number of massive stars in dense star clusters meant occasional neutron star mergers as these massive stars died, left behind neutron stars, and those neutron stars eventually collided. The enriched material from these events didn't remain localized. Supernova blast waves propagated through the interstellar medium at thousands of kilometers per second, creating expanding bubbles of hot, metal-enriched gas. Multiple supernovae in the same region created superbubbles, enormous cavities, hundreds of light years across, filled with hot gas and bounded by shells of swept-up interstellar material. When superbubbles grew large enough, they could break out of the galactic disk entirely, creating channels through which hot gas could escape into the halo and beyond. This process, called galactic fountains when the gas eventually falls back, or galactic winds when it escapes entirely, transported metals from the disk where they were created into the halo and even into the intergalactic medium. Galactic winds were particularly important for chemical enrichment on large scales. Driven by the combined effects of multiple supernovae, and sometimes aided by radiation pressure from massive stars and activity, these winds could reach velocities of thousands of kilometers per second, fast enough to escape even relatively massive galaxies. They carried metal, enriched gas hundreds of thousands or millions of light years from their host galaxies, polluting the intergalactic medium. Over time, this process enriched gas throughout the cosmic web, the intergalactic medium, which had been essentially pristine pure hydrogen, and helium from the Big Bang gradually accumulated metals. Initially, the enrichment was highly inhomogeneous, with enriched bubbles and streams surrounding galaxies, while the vast spaces between remained pristine. But turbulence and diffusion gradually mixed the metals through larger volumes. By 4 billion years after the Big Bang, the typical metallicity of gas in star-forming regions had risen to perhaps 1/3 to 1/2 of solar metallicity. This is a remarkable increase from the near-zero metallicity of the first stars. Zornisiad Solma, Star Olvema Solm, Metanishab Laun Spriting to Skeblen. A 0.2% of the mass was in elements heavier than helium. Increasing metallicity had cascading effects throughout cosmic evolution. Higher metallicity gas cools more efficiently, as we discussed earlier, because heavy elements have more complex energy level structures and can radiate energy through more pathways. This makes it easier for gas to collapse and fragment, allowing the formation of smaller stars and potentially affecting the distribution of stellar masses, stellar initial mass function. His higher metallicity also affects stellar evolution. Stars with more metals in their composition have higher opacity. Their interiors are less transparent to radiation. This affects how energy is transported from the core to the surface, which in turn affects the star's structure, temperature, and lifetime. Metal-rich stars tend to be slightly cooler and larger than metal-poor stars of the same mass. For planets, metallicity is absolutely crucial. Rocky planets like Earth are made almost entirely of heavy elements iron, silicon, oxygen, magnesium. Water, essential for life as we know it, is made of hydrogen and oxygen, organic molecules. The basis of carbon-based life require carbon, nitrogen, oxygen, and other heavy elements. None of these can exist without the heavy elements created in stars. The first stars, forming from pristine gas, couldn't have rocky planets. They might have had planets made of hydrogen and helium, gas giants, but nothing solid, nothing with surfaces, nothing that could support complex chemistry. But as metallicity increased, rocky planet formation became possible, then increasingly common. By cosmic noon, with metallicities reaching 1/3 to 1/2 of solar, conditions were favorable for forming planetary systems similar to our own solar system. Protoplanetary disks around young stars contain sufficient heavy elements to form rocky planets in the inner regions and icy planets in the outer regions, with gas giants forming where conditions were right. This meant that by 3 or 4 billion years after the Big Bang, the universe was beginning to form planetary systems that might be capable of supporting life. The chemical building blocks were there: carbon, nitrogen, oxygen, phosphorus, sulfur, and trace elements like iron and magnesium. Water could form from hydrogen and oxygen. The organic molecules could form from carbon, hydrogen, nitrogen, and oxygen. Of course, the mere presence of these elements doesn't guarantee life. But it makes life possible in a way that simply wasn't possible in the earliest universe. The first few billion years had been a period of chemical evolution, transforming the universe from a place where only the simplest chemistry was possible into a place where the complex chemistry required for life could occur. The deepening chemical enrichment also created observable signatures that astronomers use to study cosmic history. When we observe distant galaxies, we can measure their metallicity by analyzing the spectrum of light from their stars and gas. Emission lines from elements like oxygen, nitrogen, and sulfur in high regions tell us about the gas phase metallicity. Deabsorption lines in stellar spectra tell us about the metallicity of stars. But by measuring metallicity as a function of cosmic time, by observing galaxies at different distances, which correspond to different look-back times, astronomers have traced the history of chemical enrichment. The pattern is clear. Metallicity increases steadily from near zero in the earliest galaxies to roughly solar values in modern galaxies like the Milky Way, with the most rapid increase occurring during cosmic noon. There's also a metallicity gradient within galaxies. Galactic centers tend to be more metal-rich than outer regions, reflecting the fact that star formation and chemical enrichment have been more intense in the dense central regions. The Milky Way shows this pattern. Metallicity in the solar neighborhood is roughly solar by definition, but it's higher in the bulge and inner disk and lower in the outer disk and halo. This gradient carries information about galactic evolution. The halo, which formed earliest, has the lowest metallicity, reflecting the low enrichment levels when it formed. The bulge, which formed through rapid starbursts and mergers, has the highest metallicity. The disk shows an intermediate metallicity that decreases with radius, reflecting inside-out formation where the inner disk formed first and has had more time to enrich. Z-dot chemical enrichment also affects the appearance of galaxies. Metal-rich galaxies tend to be redder because metals increase opacity in stellar atmospheres, slightly cooling the stars and shifting their spectra toward redder wavelengths. Metal-rich gas produces stronger emission lines from metals, making these lines useful diagnostics of star formation and gas conditions. Dust, composed of tiny solid particles of carbon, silicon, iron, and other metals, becomes more abundant as metallicity increases. Dust absorbs ultraviolet and visible light and re-emits it in the infrared, obscuring young stars and star-forming regions in visible light, but making them bright in infrared. The dusty star-forming galaxies we discussed earlier, with their extreme infrared luminosities, are possible because of the accumulated metals that form dust. The history of chemical enrichment is, in a sense, the history of cosmic fertility, the universe's growing capacity to create complexity. From the simple beginning, just hydrogen and helium, the universe has built up a growing inventory of heavy elements. These elements made possible the formation of rocky planets. They made possible the chemistry of life. They made possible everything that followed. 4 billion years after the Big Bang, the universe had been transformed chemically. It was no longer the pristine, simple place it had been at the beginning. It was complex, rich in elements, capable of supporting intricate chemistry. And this chemical richness was continuing to grow as each new generation of stars added to the accumulated wealth of heavy elements. The periodic table was being filled in, element by element, supernova by supernova. And with each addition, the universe became a more interesting, more complex, more potentially life-bearing place. With the universe now significantly enriched in heavy elements, a new possibility emerged: the formation of stable, complex planetary systems capable of harboring worlds suitable for life. The first planetary systems had likely formed earlier, around population UA stars in the first billion years, but these early systems were metal poor and unlikely to contain substantial rocky planets. Now, during cosmic noon with metallicities approaching 1/3 to 1/2 of solar values, planetary systems similar to our own solar system could form. Let's explore how planetary systems form and why metallicity matters so much. Stars form from the collapse of dense molecular clouds, regions of cold, dense gas within galaxies. As a cloud fragment collapses under its own gravity, it doesn't collapse uniformly. Any initial rotation, no matter how small, gets amplified as the cloud contracts, just as a figure skater spins faster when pulling in their arms. The result is that the collapsing material forms a rotating disk around the forming star, a protoplanetary disk. Most of the mass falls onto the star at the center, but a small fraction, perhaps 1 to 10%, remains in the disk. This disk material is the raw material from which planets will form. Den metal poor disk, own with very low abundances of heavy elements. The disk is composed almost entirely of hydrogen and helium gas. This gas can clump under gravity to form gas giant planets like Jupiter if conditions are right. But without sufficient heavy elements, there's no way to form solid objects. No rocks, no ice, no OT to no terrestrial planets. But in a metal-enriched disk, there's a significant fraction of material in the form of heavy elements, perhaps 1% by mass if the metallicity is half solar. This doesn't sound like much, but it's enough to change everything. The heavy elements can condense into solid particles, dust grains of various compositions depending on temperature. Close to the star, where temperatures are high, only the most refractory materials can condense metals like iron and nickel, and minerals like magnesium silicates. These materials form tiny grains, just microns across initially. Verbs further from the star, where it contains water ice, carbon dioxide ice, methane ice, carbon dioxide ice, methane ice. Even further out, the most volatile materials condense. This creates a compositional gradient in the disk. The inner regions contain refractory dust. Det some distance from the star, called the snowline or frost line, water ice can condense, significantly increasing the amount of solid material available. Beyond the snowline, various other ices condense at even greater distances. The solid particles in the disk don't just sit there. They collide with each other constantly, stirred by turbulence in the gas. Chimes on collisions cause particles to stick together through electrostatic forces or van der Waals forces. Gradually, through countless collisions and sticking events, the particles grow from microscopic grains to millimeter-sized pebbles to centimeter-sized rocks. This early stage of planet formation, growth from dust to pebbles to rocks, is remarkably efficient in metal-enriched disks. Computer simulations show that within just thousands of years, dust grains can grow into kilometer-sized planetesimals, small rocky bodies, large enough that their own gravity becomes important. Zunified was Wesple explaining back count mechanism. Darlago planetesimals gravitationally attract smaller ones, growing through accretion. This process is self-reinforcing. The larger a body grows, the stronger its gravity, and the more effectively it can capture additional material. This runaway growth creates larger and larger bodies. Di in a disk, inside the snow line, the planetesimals are composed primarily of rocky and metallic materials. These accrete together to form rocky protoplanets, the ancestors of terrestrial planets like Earth, Venus, Mars, and Mercury. The process takes tens of millions of years, with violent collisions common as protoplanets smash together and merge. The final stages of terrestrial planet formation involve giant impacts collisions between Mars-sized or larger protoplanets. These impacts are extraordinarily violent, briefly melting the entire surfaces of the colliding bodies and ejecting enormous amounts of material into space. Earth's moon is thought to have formed from such an impact between the proto-Earth and a Mars-sized body called the beyond the snowline. The presence of water ice greatly increases the amount of solid material available. Planetesimals grow faster and larger here, and some become massive enough, perhaps 10 times Earth's mass, to begin capturing gas from the surrounding disk. Their gravity pulls in hydrogen and helium, and they grow into gas giants. Jupiter and Saturn in our solar system are gas giants, massive planets composed primarily of hydrogen and helium, but with rocky/icy cores at their centers. They formed beyond the snowline, where ice was abundant, allowing rapid growth of solid cores that could then capture gas before the disk dissipated. Further out, where the disk is less dense and planet formation is slower, ice giants form, planets like Uranus and Neptune that are composed primarily of water, methane, and ammonia ice with relatively small gas envelopes. And beyond them, in the cold outer reaches of the disk, the remaining planetesimals never accrete into planets, remaining as small icy bodies, the Kuiper Belt objects and comets. The entire process, from initial dust grains to a fully formed planetary system with terrestrial planets, gas giants, and debris belts, takes tens to hundreds of millions of years. The gas disk dissipates relatively quickly within a few million years, blown away by the star's radiation and stellar winds. But the solid material remains, continuing to accrete and evolve over much longer timescales. Now, why is metallicity so important for this process? Because without sufficient heavy elements, you can't form large solid cores. And without large cores, you can't form terrestrial planets or the cores of gas giants. Observations confirm this stars with higher metallicity are more likely to have detected planets, particularly giant planets, than metal-poor stars. This is the reason why planetary systems capable of supporting life probably couldn't have formed in the first billion years of cosmic history. The metallicity was simply too low. Even population, second stars, formed from gas enriched by population, the supernovae, typically have metallicities of 1/10 solar or lower. At such low metallicities, the amount of solid material in protoplanetary disks may be insufficient to form substantial terrestrial planets. But by cosmic noon, with metallicities reaching 1/3 to 1/2 solar, the situation had changed dramatically. Protoplanetary disks around these stars contained ample solid material to form rocky planets. The conditions were ripe for forming planetary systems similar to our solar system, with terrestrial planets in the inner regions and giant planets further out. This doesn't mean that planets couldn't form at lower metallicities. They certainly could, and some metal-poor stars do have detected planets. But the frequency of planet formation, and particularly the formation of substantial rocky planets, increases strongly with metallicity. The universe was becoming increasingly favorable for planet formation. The stars around which these planetary systems formed were also evolving. WBR meditative stellar lifetimes. Change slightly metal-rich stars burn somewhat cooler and longer than metal-poor stars of the same mass. Nor more importantly, the stars were calmer. The first stars, massive and short-lived, were violent objects that would quickly destroy any planetary system. But the smaller, longer-lived stars, forming from metal-enriched gas, were more benign. Sun-like stars, yellow dwarf stars, of about 1 solar mass became increasingly common as metallicity rose. These stars have several properties that make them favorable for life-bearing planets. They're stable, burning steadily for billions of years. They emit most of their light in visible wavelengths, suitable for photosynthesis. They're not so massive that they burn out quickly, nor so small that habitable zone planets would be tidally locked. The habitable zone, the range of orbital distances where a planet can maintain liquid water on its surface, is well positioned around Sun-like stars. For our Sun, the habitable zone extends from about 0.95 AU to perhaps 1.5 AU, where or in eta or at the Sun distance. Earth sits comfortably within this zone. Venus is too close, suffering runaway greenhouse warming. Mars is too far, though it may have been within the habitable zone when the Sun was younger and fainter. By 3 to 4 billion years after the Big Bang, countless planetary systems were forming around Sun-like stars throughout the universe. Many of these systems likely contained terrestrial planets in the habitable zone. The stage was set for the emergence of life, though life itself would require additional time to arise and evolve. The stabilization of these planetary systems took time. The initial few tens of millions of years after planet formation, where chaotic giant impacts were common, orbits were still settling, and the system was being cleaned of residual planetesimals through ejection or accretion. But gradually, planetary systems settled into stable configurations. Gravitational interactions between planets caused their orbits to evolve. Planets migrated inward or outward as they exchanged angular momentum with each other and with the disk of gas and planetesimals. Some systems underwent dramatic orbital rearrangements, with giant planets migrating inward close to the star, creating hot Jupiters, or outward, scattering other planets in the process. But in many systems, the final configuration was stable and long-lived. Terrestrial planets in nearly circular orbits in the inner system. gas giants in the outer system, asteroid and comet belts in between and beyond. The system that would remain largely unchanged for billions of years, providing stable environments on any potentially habitable planets. These stable planetary systems represented a new frontier in cosmic evolution. For the first time, the universe contained world's solid surfaces, atmospheres, potentially oceans. Places where complex chemistry could occur not just in interstellar clouds or stellar atmospheres, but on planetary surfaces and in planetary oceans. The inventory of planetary types was likely diverse even then. Hot worlds close to their stars, with surfaces molten or vaporized. Temperate worlds in habitable zones, possibly with liquid water. Cold worlds in outer regions, frozen, but perhaps with subsurface oceans heated by tidal forces. Gas giants with complex atmospheric chemistry. Ice giants with exotic interior structures. Some of these worlds might have developed atmospheres through outgassing from their interiors volcanic eruptions, releasing water vapor, carbon dioxide, nitrogen. Others might have captured atmospheres from the protoplanetary disk or from cometary impacts. The variety of atmospheric compositions would be enormous hydrogen-dominated, water-dominated, carbon dioxide-dominated, nitrogen-oxygen atmospheres like Earth's. On some worlds, we can only speculate which ones and how many right conditions might have existed for the emergence of life. Liquid water, organic molecules, energy sources, protection from excessive radiation, stability over geological timescales. The universe was, for the first time, capable of creating and maintaining such environments in large numbers. We don't know when or where life first arose in the universe. Dio. It might have happened during cosmic noon, on planets orbiting stars formed from sufficiently enriched gas. Or it might have required more time, more enrichment, more specific conditions that didn't become common until later epochs. In our own solar system, Earth formed about 4.5 billion years ago, and life arose relatively quickly thereafter. Evidence of life exists in rocks 3.8 billion years old, just 700 million years after Earth formed. If life could arise that quickly on Earth, it's possible, even likely, that it arose on other worlds during cosmic noon. Planets that formed 4 billion years after the Big Bang, around stars from enriched gas, would have had billions of years since then for life to arise and evolve. Any life that began on such worlds during cosmic noon would have had nearly 10 billion years to develop. By now, plenty of time for complex, even intelligent life to emerge. But we're getting ahead of ourselves. The key point is that by cosmic noon, the universe had developed the capacity to create stable planetary systems around long-lived stars, systems containing rocky planets in habitable zones, planets with the chemical ingredients necessary for life. Whether life actually arose is a question we're still working to answer, but the prerequisites were in place. The first planetary systems marked another threshold in cosmic evolution. Transition from a universe that could create stars and galaxies to a universe that could create worlds. And with worlds came the possibility, however remote initially, of life, intelligence, and consciousness arising to. Contemplate the universe that created them.